welcome everybody. I think most of you know me. Let's see. Yeah, it's quite enough, so we'll just leave the door open. For now, I'm assuming that more people will have issues with either the stairs or the elevators, or both. Let me see, who... You don't know me yet, or yes, because your name, your face. I think everybody else has seen me before, right? Okay. Well, I was so so that means you're not in the Master Bioinformatics.
I'm an exchange student.
Okay. So what's your home university?
In Italy, Padova.
Okay. Nice.
I'm doing computer science.
Yeah, and you do this as an optional course.
Yeah.
Okay. Nice. So my name is Anton Veenstra. I'm a teacher in bioinformatics. And most of the other students already saw me in the Fundamentals of Bioinformatics course, which was the previous period. I'll try to continue where Jaap left off last Tuesday on homology searching. And so I'll need a little bit of your help. So he told me he ended with fast A. And the, what's it again about? No, I don't remember the details. I need to know, so did he already go through bit scores? Previous? Okay, not at all. Okay, good. And what was the other part? So that, does this work? Oh God! Sorry, if I'm swearing, it's because I'm allergic to Microsoft software. Jaap has his slides in PowerPoint, so I'll try to minimize that. But it's so there was okay, it's rock plots. Well, that's we'll go through that. But there was the other one. Bidirectional best hit. Whoa, wrong one. There was something else. Where is it? Oh, right. Yes, low complexity regions. Okay. It's interesting, right? You spend half the morning preparing for a lecture, and then when you're in front of the audience, you just don't remember that. Can't. I'll get to that when I get to the slides. But okay. So no, now I think I can close the door. So it's about, so then the homology searching, I also couldn't access the slides because I'm not on campus. So, so homology searching 1 was about search strategies then, I guess, right? Can you give me a quick summary of what was Tuesday's lecture about?
Last thing we did was hashing.
Oh yes, that was the fast A, it was hashing, right. But before that, it can't all have been hashing.
Traceback.
Traceback. Oh, so it's basically just the pairwise alignment then, with the dynamic programming. And blast. Oh right. So from dynamic programming to the 2-hit approach and the. Yeah. Okay. Yeah.
So the systems.
Yeah. So side blast as well. Okay. Good. Then I know where you're starting from. Good. So. Today, so we'll do. There's a little bit about profile scoring. Most of today will be about the statistical scoring of these hits, right? So you've heard about bit scores and e-values and so on. We'll go a bit into the details of the theory today, and basically the statistical background where these scores are derived from. Something to think about in terms of what does homology mean, something about validating homology search methods, which isn't an entirely new topic to most of you, but we'll revisit that, and then some practical issues for, well, the particular examples are from BLAST, but these relate to basically any homology search method that you might use. So to start with the big picture, why can you do why do you want to do sequence searches? I'm sure Jaap has mentioned this in every lecture up to now, right? He does, yes. Right, because you have a common ancestor, sequences diverge, but due to evolutionary pressure, both the structure and, most importantly, the function remain the same. Yeah. Well, how similar the same is that can differ between cases, and how dissimilar this is also will differ between cases, right? But this is sort of the landscape that where sequence searches are useful, right? Okay, so and then if we know, I'll just to hammer in the point once more, right? If we know the function for this protein and we're interested in the function for our sequence, and we know we can find a similarity here, then we can assign function G to our unknown protein of unknown function, right? I'm not going to go. I can lecture half an hour on this slide. So I won't do that. Okay. So this is also not new to most of you, but the best way to do sequence searches is to use profiles, right? And you've already seen it done, or Jaap explained to you how it's done in using SciBlast. You've also been told a couple of times already that HMMs are actually a better way to do it. There will be lectures and actually even an assignment on HMMs later on in this course. But in any case, you're searching with your query sequence or a query alignment or a query profile or a query HMM, depending on exactly which method you're using, against a database. And then also in the database, the database could consist of single sequences or profiles or actually HMMs. Right? Do you remember a database of HMMs? Maybe? Or alignments? PFAM? Yeah? Okay. Why is that? Why does that make sense? Right? Because I'm interested in this sequence. Right? I want to find this one, which is similar, for which I know the function. Why do I need a profile? Why? Because basically, you mentioned PFAM, right? So it's protein families. But now then I'm searching with protein families. I don't want to know something about a protein family. I want to know something about my sequence X. Why does that make sense?
Because we sequence have similar structure and function, so say something about
Right.
the sequence.
Yeah, that you all didn't get that. Yeah. So because what you hope to see is that within this family, even though sequences might diverge, the structure and the function should have remained consistent, right? So if you can't find a direct hit at the sequence level, if you compare the families and you see similarities at the family level, then you can still see the underlying structure and function similarities, even though at the sequence level they might have diverged beyond recognition. Okay, so if you do the, you've seen the other paper, most of you have seen the other paper, but here you can see, so BLAST is sequence, SciBlast is sequence profile, Hammer is sequence HMM, I think, HSpread is HMM. So if you just take those as an example, so BLAST is pretty low, SciBlast, and then HSpread. No, HSpread over here, the black line, right? So this is quite a big difference in terms of the number of true positives that you find here, right? So much better sensitivity. Okay. Now, what you have used, but you haven't. Let's go back. Oh, that's forward. Let's go back. Right now, you're searching for sequences, and you align them. You get a score, right? A higher score means it's a better alignment, right? It's a better match. But what you actually want to know is whether it's a significant one. Just because two things might have a good score, which is still not significant. Yeah? Or the score might compare weakly against another score, but if you align if you align two relatively short proteins, or if you align two very long proteins, which one will get the higher alignment score? Yeah, right? Because you have more matches to add up. Yeah. Even if they're more divergent, the long ones, then they'll still probably have a higher score. So you can't really compare scores between different alignments. And also different methods might actually use quite different scoring formalisms, even just Blossom matrix or HMMs, they all have very different metrics, right? And in the end, you don't care too much about the actual scores. You want to know something about the significance, right? You have two proteins aligned. Are they actually? So what does significance mean here? If you have an alignment between two proteins, what does it mean if you say that they're significant? They're homologous. But that's hard to quantify. So how do we do that?
Functional.
Yeah, that's even harder to. I would say that's even harder to quantify than.
Could create random scrambled sequences, maybe
Right.
thousands of them, compare them, and then see how many of them are larger, equal
Yeah.
to your fonts.
Exactly. Right. So that's on the slide already. Yeah. So no, that's fine. There's a difference between looking at a slide and thinking about what I'm trying to explain. So the significance here is whether your alignment is actually different from random, and different in most cases meaning better. Yeah, it's quite hard to be worse than random. So if you say different from random, it means it's better than random. And one way to get this sort of background is to say whether is to look at what the scores would be if you randomize your sequences. Right? You randomize your sequences, you align them. That's what you'll. If your sequences were random, it hits. You should get similar scores if you randomize the sequences. Right? If you don't, so if you get a different score for the true sequences versus the randomized ones, then it's not random. That means it's significant. Okay. Now, so this is the basic way how you do that. So you randomize them. The problem is the randomization is quite slow, right? So if it takes half a second to calculate the score for two alignments, it will take, to get a good estimate, you typically need several hundreds or thousands of randomizations. So it will take, just calculating the score will take 1,000 times longer, but then you also have to do the randomization. And so it's relatively quite expensive. If you need to do this for a database search, where you're comparing one sequence against millions, then well, maybe you don't have to calculate the significance for all of them, but you would still like to be able to get something quite quickly. Right. Okay. So who isn't sure about what a z-score means? Okay. This is a nice graphic for it. So I'm not quite sure if this is a good representation of a, what's the word again? A normal distribution, because I don't think it's particularly, I think it's too round at the top. But anyway, this is a cartoon representation of a normal distribution, right? And there's some average value that's much more likely, and then you have some distribution around it, and more extreme values either to the negative or to the positive become rapidly less likely. Yeah, and then so you can compare if you have whatever data it is from similar setup, then you can compare these values straight away. But what you basically do for a z-score is you say, well, they all. If you have a distribution of values, you can calculate the average. So if you now, or the mean, if you subtract the average, then your average will be 0. Right? If the average was 5, you subtract the 5 from all the data points, then the average becomes 0. Yeah, you just shift everything. And then you divide it by the standard deviation. Then your standard deviation, which is roughly the width at half maximum in this plot, will, oh, it's not quite true. It's over here. This is the standard deviation. Then actually your standard deviation becomes 1. Because if your standard deviation was, let's say, 3.5, you divide everything by 3.5, then your standard deviation becomes 3.5 smaller, which means it becomes 1. Yeah? So that's how you derive a z-score. So you can think of a z-score as how for a given data point within a distribution, the z-score tells you how far it is away from the mean. Yeah? So if it has a z-score of +1, it's 1 standard deviation above the mean, which is actually still quite likely. Yeah, +1 standard deviation is still quite likely. +2 standard deviations, it's quite significantly less likely, right? +3, this doesn't go to 0 at +3. It should actually run on. It actually goes on quite long, but it just goes gradually to 0. But +3, well, you can see the percentages here. Between plus and -3 standard deviation, you get 98% of your data, right? So if your data has a standard deviation that's higher than +3 or smaller than +1, you know it's only 2% likely, right? Okay. Now, you can use it for all kinds of things like outlier detection and so on. But in this case, we're going to use a distribution from a random sample that gives our the random expected value, and then for the real data, we calculate the standard deviation with respect to the random, and then it should be significantly different from random, which means it should have a high. Typically, in our case, our alignment scores will be higher for the real data than for the random, right? So you will have a high z-score. +5, +6, +7, somewhere over here. Yeah? Then you're sure that it's not random. Okay. Right. So, coming back to BLAST. So we want this score to find true positives. And as I already mentioned, if you just score the alignments, it's dependent on what scoring system you use, your exchange matrix, and your gap penalties, and so on. But it also depends on what database you're searching in. Right? If you're searching in a big database, then of course it's easier to find random things, and also random might look slightly different in one database compared to another one. Yeah? If you have a database of let's say DNA sequences, but it's a database. I'm not sure that's a good idea. Good comparison. Think about proteins. If you have a database of transmembrane protein sequences, they might have a different sequence composition than soluble proteins. Yeah? So there's probably better examples to give here, but that's the one. Yeah, so it depends on the database, and particularly the size. Okay, so how do you do this? So where did the, oh right, yes, sorry. So z-score would be a nice way to do it statistically, but this is slow. So there's a better way to do it, which actually takes advantage of the fact that you don't have to do the explicit randomizations of your sequences. You can actually calculate what, for a given database, what your distribution of expected random scores would look like. So that's what I'm trying to explain to you a bit. Okay. So there's a couple of things that you need to do. The first thing is to go away from the raw alignment scores, and that's used in this, shown in this formula. So this is the raw score, which comes from whatever way you made your alignment, and then you need two parameters which you can consider as a given. Already quite a while ago, 20 years ago, these Altschul and Gish, they normalized these different scoring schemes and found lambdas and k's for the most common one, like Blossom and Palm and a few others. Also some that were used then, but they're not really used anymore. there's a way to actually fit them or derive them from your data, but that's beyond this lecture. So if you have your lab.uk, you can convert your alignment score into a bit score. The nice thing is that you only have to have, once you know how to do this for a given scoring scheme, you can convert it easily, and then you have something that you can compare between, it becomes independent from your scoring scheme. Okay, so where am I going? I'm missing a step in my head, so sorry, I have to recalibrate. Because I know how to get from here to here, but there's several slides in between. Sorry guys. Okay. That's what I always do. I've already explained most of the stuff that's on the next slide. Okay, that's confusing if you then look at the next slide. That's not new. No, it's not new. Okay, so this was the idea for a z-score. If you have a z-score, you can calculate a p-value, right? P-value meaning the probability of obtaining a result by chance, and obviously lower p-value is a hit, right? Less likely to be from derived from chance. Now, what we're actually interested in here is the probability. So, when looking in a database of a given size and sequences, and I'm actually going to write the formula on the board. This is the probability of finding in a database of size n to find a hit with at least how to say this, minimum score, yeah. With a score of x or higher, right? And you can calculate that as exponential n times I'll have to figure out whether it's p as there's always one step more. I've done this lecture before, but it's been a while, and there's always one step more than you think there is. Because where do we get? I should actually teach myself to always write out the formulas before I do the lecture. We'll get back to this. So if you have right, yes, now I get it. Yeah, sorry. So if you have the probability of getting a score higher than x for a given sequence, right, then for a database of size n, you have an exponentially increasing chance of finding at least one hit with that score, right? Yeah, makes sense?
Just to clarify, the probability above the E, that's the probability of what again?
This is the probability of finding, just for a single sequence, to find a score that's higher than X. So for a single pair of sequences, to have an alignment score higher than X, right? But then if you do this for a database search, you have to multiply that by the size of your database, and then it goes exponential, right? No? Okay. So yes, so you have to go from the single comparisons to the whole database, and so just to break this down into steps. Here we have our probability of finding a single pair with a score higher than X, but then over a database of n sequences, you get your expectation value, right? This is your e-value as you have it in BLAST. Now we still have to figure out how to get this one, right? Yeah. But just to go into this e-value, let's say our e-value is 0.01, right? Then we expect that if we search in our database 100 times, on average, by chance, we'll find one hit with a score of X or higher. Yeah? Okay. Then if the e-value is 5, that means for a single database search, we already expect to find 5 hits with a score of X or higher. Yeah? Which means that this hit is actually not significant. Although if it's your only hit, yeah, you might still be happy with it, but you have to be careful then. Okay, so it's not obviously a good one. Let's put it that way. You have to think about, but this is a pointer for later. I think not even later in this lecture, but just later. What happens if you have 100 hits with an e-value of 0.01 in your results? That is, it's not quite 100 independent searches, because they're all from the same query, but you would expect that this is not strictly true, but it is related. You should assume that not all of your 100 hits with an e-value of 100 are significant. You know, by chance, one of them is probably going to be non-significant. Yeah? No?
Sorry, can you repeat?
What?
Well, if tossing a 6 on a die is significant, right? You toss your die once, you have a 6. You're happy, right? If it's in a casino, you bet at 6, you're happy. But if you toss the dice 30 times, you get 5 6s. That's what you expect, right?
No?
1/6.
Oh, okay.
Yes. Yeah. So if you have 6 results, and your random chance of finding something is 1/6, then one of those 6 will be random. Yeah? Now there's a slight difference between that chance and this chance with the e-value, but you have to be careful, right? 1,000 hits with an e-value of 0.01, expect about 10 random hits in that set, but you don't know which ones. Yeah? Okay. Now, how to get to this formula? I started with the story of the z-score, where you actually use explicit randomizations, but you can actually dive into some theory, or somebody with enough statistical background, a bit more than I have, can dive into theory and find this distribution, extreme value distribution. It turns out that this is the distribution that you get for random alignments.
Coming back to what you said before, so if for instance the e-value is 0.01 isn't it related to the p-value that if you have p-value of 0.001, that there is still a 1% chance that you took it from a null distribution? Is that what you're saying?
Yes, that's related, but but now it's not for a single pair of aligned sequences, but it's for a search through a whole database, right? So because here you have the p-value, right? So that's the probability for a given score threshold of finding a sequence that has at least that score, an alignment that has at least that score, right? But if you repeat that 10 times, if you do this over a database of 10 large, then of course your chances of finding, you have to multiply by 10. Sorry. Is this getting? I'm not sure if I'm being very clear.
Okay, I was just expecting, because even if you have 10 hits, the chance that they are actually taken from the null distribution stays the same for each of them, no? It doesn't mean that if you have more e-value hits, that is suddenly...
Yeah, it's per hit, yes. But if your p-value is 1/10, then you have a 10% chance. You expect that 1 out of 10 will actually still be from your random distribution, right? You don't know when it happens, but that means if you do 10 of those, 1 of those 10 is likely to be a random hit.
Okay.
Yeah.
Yeah, but still, probably this is the same for each of them.
Yes,
Yeah, okay.
for each of them the probability is the
Okay,
same,
okay.
but you have 10 of them, then it becomes increasingly likely that one of them is really not a good hit. Yeah?
Thanks.
Okay. Right, so this is what this extreme value distribution looks like. I'm not going to go into the theory behind that. This is the general shape, but it has two parameters. One is the mu, which is actually the position of the peak, and the other one is the lambda, which is actually the steepness. But you can actually fit it to real data, and here I don't see what the real data was, but I came across. I don't remember if it was in the, I think it was in the book, where they have an example of alignments of cytochrome C, I think, protein, and then but it looks very similar. So you make all possible alignments of cytochrome C proteins with each other and with database sequences. You get a quite big distribution of scores, and then you can fit your extreme value distribution on that set of scores. Right. So, and it might look sort of Gaussian to you, but it's asymmetrical, right? So if you, the Gaussian is actually the Gaussian is just if you have the single exponent, you leave this one out. But this is a double exponent. It's a bit funny notation maybe, because you say x here and e there, but they actually mean the same. Yeah. Okay. That makes it asymmetric. Which for these scores is actually because you expect random distribution to be skewed towards low scores. They're not symmetrical around 0 or something. Okay. So now what we need is now we can, instead of doing explicit randomization to get, that doesn't really work well on the board, to estimate this probability, we can actually get it from this extreme value distribution. And so then we get this. Now it says e-value. I'm not sure if that's correct, because there's this n missing. Question?
Is a prior probability, so
Which one's the prior?
we could think about the p-value as
I'm not sure if I can cast this into priors.
Because we use like distribution.
Yes, yes. You can think of this as your your uninformed distribution, right? This is your null model, and then you get your you can view your alignment as being the information that you gain. Yes. I always find that very difficult to reason about, which is probably why I never went into statistics. But it's very useful if you can do it. Okay, so so now we can calculate this p. It says e-value, but there's an n missing, and then you have a formula. So remember the k and the gamma that appeared on the previous slide. Those are the same ones, and you can actually calculate the mu, so the position of the peak, from your k and your gamma, right? And then there's two other parameters that appear here, which you also know because m is the length of your query and n is the length of your database. Yeah, if you have a query sequence, you can easily calculate how long it is, right? And if you're searching in the database, well, for each given database, you only have to count how big it is once. Right? Okay. It doesn't say here, and I haven't looked it up, whether how you count the length of your database. Probably the sum total of letters in it, but it could be the total number of sequences. I don't know which one you should use. It's probably somewhere in the paper, but I couldn't find it. Okay, so so why would this actually depend on? Well, it's easy to see why it depends on the length of your database, the size of your database, right? Yeah, it does. Because the bigger your database, right, the more sort of random things you might expect to find there. Okay. Why would it depend on the length of your query?
Because your shorter query has higher probability of finding a hit.
Possibly, but can you elaborate that?
Yeah, like if we search for a hit for a query like AC, for example.
Yeah, so a very short query. Yeah. Okay. Yeah. So it's normalizing over that, right? It's also to make sure that if you have hits of different lengths, that you can actually compare them, right? So that an e-value of 0.01 roughly always means the same thing. Okay. And then, yes. Now, so this is what is then if you substitute it over here, then you get this. So what? This is oh yes, this is one exponent. That is the other. Now the k, m, and n are already filled in, and the final trick that they do, because people say this is well, calculating an exponent is actually relatively expensive. For larger larger x, the exponent of the exponent is actually almost the same as the exponent, or minus e to the minus x. So you can approximate this with e to the minus x, and then you get this formula. Right? So now this formula allows you to go from for a given score threshold. Now I've lost. This should depend on the score, but I don't see where that ended up.
Isn't the score X?
That's a sorry. Yes, that's a threshold. Yes. Okay. Yeah. Thanks. Yeah. Okay. So that's how you calculate this probability of finding a score larger than x, and then from the other one there. from that, probably I also learned that I shouldn't type formula or write formulas off the top of my head, because that's right. So the e-value of a hit with a hit with a score x on a database of n, that's n times your p-value of finding an aligned pair with a score higher than x, right? Okay, now back to where we were. Over here, yes, right, okay. So, so common thresholds would be between 0.1 and 0.001. If you have a lower e-value, you get less false positives. Yeah, it means fewer hits that aren't really matches, aren't really homologues. But of course, you also increase the number of false negatives, meaning that there's real homologues that you fail to find. Yeah? Right, and we'll come back to that in the later slide. Now, just to wrap that up, so if you do explicit scrambling of your sequences, you can calculate the z-score, and then from the z-score you can calculate all the rest. This is slow, but you don't have to worry about the a priori parameters of your database. But doing it with through the extreme value distribution is much faster, but it depends on your database, right? So you need to calibrate your calculation each time you switch the databases. And there are some assumptions in that, in how this is calculated. So, for example, it doesn't work well for very small databases.
The z-score or p-value?
Sorry?
The z-score or p-value?
The e-value. Yeah. Not the z-score. Well, it does, because you do an explicit. Depends how you do it. Because randomization also depends on your null model. But if you just do a plain randomization, then you can just do it for a match, a pair of aligned sequences, right? If you call that a match, you can randomize them and realign them, and then get your distribution of scores. You don't have to know which database they came from. Yeah. Yeah? Okay. Now I need to see. Right, okay. So we're inevitably going to, wait, oh, sorry, skipping one slide. You've seen slides like this, right? But, you know that when you have, sorry, this is just to show that when two sequences that you're aligning are more distant, you're likely to get more errors, right? So over here you have the number of identical residues between the two aligned sequences, going from 100, where it's obviously very easy to align, and down towards, well, let's say 10 or so. And this is the percent of correctly matched residues. And then of course you need a reference to say which ones are correct or not. That's a different story. You see that, let's say, going from 100% identical, which is really trivial, obviously, down to, let's say, 60%, maybe 55%, it's really still very easy, right? So if half your residues are still the same, then the alignment is going to be very difficult. Even down to 30%, you can see that in most cases you'll still have 80 to 90% of the alignment correct. Yeah? Only if you go below this, then it very, very sharply deteriorates. Yeah? So at 20% identity, you're down to 50% roughly accuracy in your alignment. At 10%, you're too close to random. It's going to be next to impossible. What would be random? What would be your random percentage identity between two completely unrelated sequences?
5%.
You say 5%. Anybody has another idea? Why?
It depends on the sequences, if they are proteins or nucleotides.
Is it, yes, if it's nucleotide, what do you expect?
It's about 25.
25%, right?
If it's proteins, about 5.
It also depends on your on the distribution, right? But if you assume an equal distribution over your alphabet, then it's 1 over the size of your alphabet, right? So for 20 amino acids, 1 in 20 is 5% identity, but so 10% is really close to random. Yeah? I would